Hello students, in this video we're going to wrap up our initial vector discussion by talking about addition, subtraction, and rotation both in rectangular and polar form. So let's first talk about addition. Well, addition and subtraction are actually the same thing because subtraction is basically adding the negative of the second vector. So let's just talk about addition in general. Addition is very easy in rectangular. So let's say you have two vectors, okay, a comma b, okay, and another vector, let's say e comma f. And if you want to add them together, let's call this u, let's call this v. So u plus v is simply adding the respective components together. So a plus e, comma, b plus f. Okay, so and graphically you can kind of see that if the vector u is like this and adding v to it, when you add two vectors, you're putting the tail of the second vector to the tip of the first vector. So let's say v is pointing in that direction, and then the final vector u plus v is indicated by this dotted one. And you can see readily that if u has a component of a and b, and this one has a component of e and f, then the final vector is simply a plus e, and the y component is simply b plus f. Okay, so that's pretty intuitive. But what about if you're given two vectors in polar form? So instead of u given in rectangular, I'm going to say it's going to be 5 units and 35 degrees. And then v is going to be 7.5 units at 120 degrees. Can you just add them together? So can you say u plus v is equal to 12.5 at 155 degrees? That would be very much wrong. So pause the video, think for a second why that is not the case, and then we'll check. Okay, to see why, I've plotted here the vector u and v. So vector u has a unit of 5 units. So this is my u vector, and it's at 35 degrees with the positive x-axis. Okay, and then vector v has a length of 7.5 units, and then is at 120 degrees. Okay, so to add the two vectors together, what I've done is I've translated the initial vector to where the orange vector is in that position, and then again when you add two vectors, you put the tip of the first vector to the tail of the second vector, and then the end vector is what I've indicated in the dotted line. And we can clearly see that that vector doesn't have a length of 12.5 units. Okay, I know I'm only approximate in scale, but to be sure, is not going to be at 155 degrees. In other words, this angle here, okay, is no way 155 degrees. It's clearly less than 90, in fact. So, how are we going to go about doing that? Okay, so what happens then is when you're adding vectors in polar, you have to first convert them to rectangular form first. Okay, so here are the steps 1, 2, and 3. Step 1 is you need to convert both vectors, u and v, to rectangular representation. And there's an early video on how do you convert from rectangular to polar and polar to rectangular. And then once they're both in rectangular form, then you just add their respective components. And that would be the answer. Sometimes the problem may ask you to convert it back to polar, in which case then you go through the reverse process and convert it back to polar form. Okay, so unfortunately there's no easy way to add vectors in the polar representation without going to the rectangular form first. Okay, so let's talk about vector rotation. If I'm given a vector u equal to 3, 2, and can you give me what vector it would be after I rotate it by 90 degrees clockwise? Well, so I plotted out the original vector. So this is going to be u with the component 3, 2. And if I want to rotate 90 degrees clockwise, it's going to end up in the position where I've highlighted in purple, right? And here is an easier case where we can take advantage of the slope formula that we've learned in algebra. In other words, if I know the slope of this line, okay, let's call that m, then I know a line that is perpendicular to it at 90 degrees must have the slope of -1 over m, right? Because the product has to multiply together to be -1. So in this case, I can use the coordinates 3, 2 for me to calculate the slope. So m in this case must be equal to y over x, rise over run, so 2 over 3, which means the slope for the purple line would have to be equal to -3 over 2. Okay? So it's going to go 3 down, okay, and 2 over. Okay, start over. So here I have plotted out in the xy plane the vector u, so it has 3 units in the x direction and 2 units in the y direction, as indicated in blue. And then if I want to rotate it 90 degrees clockwise, that means it's going to be in the direction where I've drawn in a purple arrow, right? In this case, it's somewhat easy to do it in the rectangular coordinate when you're rotating by multiples of 90 degrees. And the reason is the following. I know in algebra that if this line has a slope of m, okay, if it has a slope of m, then a line that is perpendicular to it must have a slope of -1 over m, because the slope of 2 perpendicular lines multiplied together has to be equal to -1. And so I can take advantage of that fact, and I can calculate the slope of the original vector u by using its x and y components, right? The slope, in fact, is equal to change in y divided by change in x. Change in y is 2, change in x is 3, so it has a slope of 2/3, which means the slope of the purple line must be, so its slope must be equal to -3 over 2. Okay? So that means it must have 2 units in the x direction and -3 units in the y direction. And that gives me a direction of what the rotated vector needs to be. The only thing I need to make sure is that the length is the same. Well, since the x and y components are still 3 and 2 respectively, okay, by Pythagorean theorem, the length of u, the one in blue, must be the square root of 3 squared plus 2 squared. And the length of the purple vector is also the square root of 3 squared plus 2 squared. So therefore the length are the same. So therefore I can conclude that the purple vector is the 90-degree rotated vector of u. So if I call this v, so v would then have the component of 2, -3. Okay, it's 2 units here and minus 3 units in the y direction. So that one is relatively painless. Now what if I want to rotate it by non-increments of 90 degrees? So let's say I change the problem and say I'm going to rotate you by 87 degrees counterclockwise, as indicated in the diagram here. Okay, so this I want to rotate it 87 degrees that way, resulting in that purple vector v. What do I do then? Well, in this case, we cannot use the rectangular coordinate and do this slope exchange in order to help us to find out what the rotated vector is. In this case, we have to go through the conversion to a polar vector and then a polar representation, and then do the rotation, and then find out what the final vector is going to be. Okay, so step one, let's convert u to polar, and pause and then check our answers. Okay, so is that what you got? So we need to find r and theta, and recall from an earlier video that we find r by using Pythagorean theorem. So r would be equal to square root of 13, and we find theta by using the inverse tangent ratio, 2/3. So theta we calculate is 33.69 degrees. So now that it's in polar coordinate, then to rotate it is relatively straightforward, because what we know is that this angle for u was 33.69. So therefore the angle theta for v must be equal to 87 plus whatever the original value is, right? Okay, so if you add the original 33.69 to 87 degrees, you got 120.69. And r is unchanged because you're only rotating the vector, so the length of the vector does not change. So that is how you do step 2. And the final step is simply write down what the polar representation of v is. And it has a length of 13, square root of 13, so r is root 13, and the angle of 120.69. Okay, and if the problem asks you to convert it back to rectangular, then yes, you can do that, and you can refer back to an earlier video for that. Okay, so let's summarize. We have vector addition and vector rotation. So let's first talk about addition first. And addition in rectangular form is relatively easy. You simply add the x and y components together separately. That's what this square is. But in polar form, you have to do 3 steps. Okay, you have to first convert to rectangular, and then you have to add the components in rectangular form, and then the third step is you have to convert back to polar. Depends on whether the problem asks you to do so or not, but at least you have to go through the step of converting each vector to a rectangular form before you can start adding them. Now what about the vector rotation? In vector rotation, if you happen to be in rectangular representation, then unless you're rotating by steps of 90 degrees, which you can use then the slope relationships to help you figure out the rotated vector, otherwise for any arbitrary angle of rotation, you would have to convert to polar first, and then add or subtract in the degree of rotation, as the case might be, whether it's clockwise or counterclockwise, and then convert back to rectangular. So it's a bit more cumbersome. Whereas if it's already in polar, then all you have to do is just add in. Whereas in rotation, then if it's already in the polar representation, then you simply add in the degree of rotation and leaving r unchanged because you're only rotating the vector, so the length of the vector is unchanged.